Hi folks, welcome back to another physics lesson, and this is part 2 of 3 to do with our particle physics. And today we're going to look at something really important called beta decay, which is to do with beta radiation. And we're going to state the products of beta decay, and we describe how the beta decay led to the discovery of neutrino. So there isn't really any calculations today, but there is going to be a wee bit of note taking and a bit of summarization from you. So a wee joke here for you to read through, folks. Pause the video and have a read of that cartoon there, folks. So what is beta decay? Well, beta decay is when a neutron is converted into a proton, which allow new elements to be made. And again, this will tie up with our radiation part of the topic. But if you've done chemistry, you might know that the proton number is the number that defines an element. So for example, hydrogen has a proton number of 1, and only hydrogen has 1 proton. Helium has a proton number of 2, so it has 2 protons. So if you are able to convert a neutron into a proton, you could convert a hydrogen atom into a helium atom. Now, one of the ways this is used most commonly is in something called carbon-14 to nitrogen-14. Now, this is really important because if you've ever studied history, you might have heard of them talk about radiocarbon dating. And what they're really doing is they're measuring the decay of this carbon-14 into nitrogen-14. So without beta decay, we wouldn't be able to do carbon-14 radiocarbon dating, and we wouldn't be able to date how old historical objects are. Now, you don't need to know this equation off by heart, but you do need to know that beta decay produces certain products. So this is what I want to know. So if you could make a note of this slide here with the definition of beta decay and also the products of beta decay. So beta decay also produces electrons and antineutrinos, and the electrons emitted as beta radiation, a flow of electrons. And this is why it's called beta decay, not a neutron decay, which you would think would make more sense. Now, what happens in terms of the quarks? Well, again, first of all, could you write down this equation? Because we will be using these type of equations later on for radioactive decay. So this tells us, hopefully you can read it, a neutron going into a proton plus beta radiation, you could really just put an electron here, and an antineutrino. So what happens is that in a neutron, we have up, down, and somehow one of these down quarks changes to an up quark, and that gives us a proton. And in the process, we release an electron, and we also release a neutrino. Now, you're not expected to know how the down quark changes to an up quark. You're not expected to remember this equation, although if you are given it, I would expect you to be able to tell me there's a neutron, proton, an electron, and an antineutrino. So, how did beta decay lead to the discovery of neutrino? Now, this is a little story that you need to be able to tell me or tell your friends, and this is where the examination comes in. So beta decay was evidence that led to the discovery of the particle called neutrino. Okay, so there's the reaction there. Now, one of the ways this happened was that physicists could measure the energy before and after the reaction, and they found that they were not the same. And this suggested there was an unknown quantity or a particle, because remember, energy suggests mass, and we'll talk more about this when we do the radiation topic. But we've already come across it before, because remember, we can calculate the energy of particles in terms of electron volts, can't we? So remember, we had this unit for electron volts where we did EV over C squared. And we said this could be a unit for mass of a particle, wasn't it? So because there was some missing energy, and we couldn't account for it by just saying it was converted into heat or converted into sound, that suggested that there must have been a particle that we don't know about. And so once they realised this, they could then do experiments to finally prove that it was actually an antineutrino, or therefore a neutrino. Now, neutrinos, as you know, has a zero charge and they're a fundamental particle. I hope you remember what that means. And one of the key facts about neutrinos is that they're very, very boring. They don't like to interact with anything because they have the zero charge. And we reckon there's about 65 million neutrinos pass through your thumbnail every second. And these are neutrinos coming from the sun. There are three flavours of neutrinos, which you've come across already. We have electron neutrinos, muon neutrinos, and tau neutrinos. And these are all leptons, remember, which means they are not made from any quarks. And again, all three of these have a zero charge, so they're all very boring. They don't like to interact with anything else at all. I would make a wee note of this because it is important to know about our three different neutrino types and their charges. And as I said, this makes them really hard to detect them as they don't interact with anything at all. How do we detect them if they're so hard to detect? Well, one way they do them is by having these big massive containers with certain chemicals deep under the ground. So quite often physicists will use mines that are deep into the ground, set up experiments to try and detect these neutrinos, but usually when I say detect them, they might detect one or two per year. They are really, really, really difficult to kind of pin down. And finally, so to summarize all of this, there's a fantastic video by Fermilab which explains the whole discovery of neutrino in a bit more detail. So I would definitely recommend you watch this video. I'll include the link in your assignments, and I want you to be able to write down the story and summarize it in your own words. So what's really nice about this one is there's no calculations at all.